so that
My first name, my given name is Gesche, and my last name is Pospich.
Okay, thank you. So we are just waiting for the audience to join, and then we'll start.
Yes. Okay, thank you.
She has cut me off. Here's my microphone is unmuted. Hello.
Hello,
This
Professor.
is Dr. Kulkarni speaking.
Yeah,
Kulkarni
Professor
from
Arvind
Bangalore.
Kulkarni.
Yeah. Good
I'm
afternoon.
able to read your name, but I'm not able to see you.
Yes, my video is stopped. Oh, I don't know. I'm coming.
Right. Welcome, sir.
Yeah, really stop my video. And
দেখিয়ে দিই যে আমরা আছি।
Hello.
Hello.
Am I audible, Sapna?
Yes,
Yes, you are
Rekha,
audible. Yes, you are.
Yeah. See, I have started the meeting and it is also live on YouTube.
All right.
Huh?
Ma'am,
Yeah.
have you shared the YouTube link on IAPT group also?
I will share right now. It is not necessary because our Zoom has a capacity of 100.
Okay.
So I will share that. Don't worry. But
All right.
yeah, it is. I will check again whether it is live on YouTube also, and then share the link also. And yeah, maybe in 5 minutes I will have to leave. Here.
All right, ma'am.
Yeah.
You'll make me host now that time.
Just a minute. First, let me. I think this waiting room. Why it gets disabled, enabled? I don't know. Okay. Now chats are also public, and also you can. Anybody can join because there was a waiting room earlier.
All right.
Now tell me who all I need to make co-host first. Our guest, I think she will be the co-host, right?
Yeah.
Yes, too. Fine. I don't know. Still, that waiting room is.
Namaskar, P.C. Deshmukh, sir. Good evening.
Namaste.
Good evening, sir.
Namaste. Good evening.
Namaskar, sir.
Namaskar, sir. I think Professor Ghatak
Hey,
also has
Deshmukh, sir.
joined. Professor Ghatak also has joined. Arvind Kulkarni, sir, namaste.
Yes,
Kulkarni
namaste.
sir has
Namaste.
joined, yes.
Sir, I'm in Bangalore.
Yes, I'm in Bangalore.
No, I'm also in Bangalore.
Oh, you are in Bangalore. Great.
There is a
Then we could meet up sometime.
No, sir. I'm leaving for Romania tomorrow morning.
Oh,
4
tomorrow morning.
4 a.m.
Okay.
Yeah. The Indian team is leaving for International Junior Science Olympiad. So I'm going with them. Another 4.
Well, best wishes to you, Rekha.
Thank you, sir. Thank you so much. Thank you.
Come back winning all the medals.
Thank you so much. Thank you.
Fantastic.
Yeah, students have just left actually to their rooms. Otherwise, I would have made them, see all of them. The team, 6 students. We have just finished talking to them. They have to pack up things, no? 4 o'clock in the morning, 4 a.m.
No,
Yes.
We will be leaving. Yeah. So that's the reason, right? But let me check in between whether live YouTube is live, and then I will leave because some people are waiting for me here.
All right, all right. So you have made me host and the speaker is co-host, and you can make Professor Arvind Kulkarni either
Yeah,
co-host.
yeah. Let me first check the YouTube etc. is running properly, and then I will leave.
All right, ma'am. All the best.
Thank you so much. Thank you.
Professor Aluwalia has also joined.
Yes. I have the question. Do you see my presentation already? Or
Yeah,
We see a lovely mountain.
Okay. Then I have to check to change that. Okay. Thank you. Share. I will. Okay. Then I will have to change that.
good evening, sir. Aluwalia, sir. Good evening.
Say,
Okay.
Professor Aluwalia. Good evening.
Okay.
Good evening to everyone.
Good
Namaste.
evening, sir. Good evening. Sapna, YouTube is working properly. I
All
have
right.
shared the
Thank you,
link.
ma'am. Thank you,
I have
ma'am.
shared the link also on the IAPT.
All right.
So absolutely no problem. Professor
Great.
Gesche, please excuse me. I have to leave. And I welcome you
Have a nice
for
eve-
the
Have a nice evening. Goodbye.
very, very, very warm welcome and thanks.
Thank you very much for your kind invitation. I'm very
Eh,
happy to be able to
Thank
speak
you.
to you.
Yeah.
So we can see your presentation now.
Yes,
Professor,
fine.
we can see your presentation.
Thank you.
Yeah. So with the permission of Aluwalia sir is there. Sir, can we start?
Oh, sure. Yes.
Yeah.
Uh,
So we'll start. People will keep on joining us. And let me
Sapna,
start.
I'm making you host now. So all
Oh, all
controls
right.
will be with you.
All right, ma'am.
Thank you.
Thank you.
Okay. Yeah.
Yeah. So good evening and welcome everyone. It's both a pleasure and an honor to welcome you all to the Indian Association of Physics Teacher PER lecture series. IAPT is deeply committed to promoting excellence in physics education, supporting the professional development of educators, and advancing the field of physics teaching and learning. I'm sure that the insights and knowledge shared on this platform will inspire us all and equip us with the tools to make a meaningful impact in our classrooms. Today, we'll be having the 18th lecture in this series. And it's my honor to extend a warm welcome to Professor P.K. Aluwalia, the distinguished president of Indian Association of Physics Teachers. I must mention here that his constant support and leadership have played a pivotal role in advancing our initiatives. A special welcome is also extended to Ma'am Rekha Ghorpade, the Secretary of IAPT. I welcome our distinguished speaker, Professor Gesche, Professor of Physics Education, Daristan Technical University and Chair of Physics Education. Professor Pospish has extensive expertise in both the theoretical foundations and practical applications of quantum mechanics. She will be discussing the fundamental field of quantum physics and quantum technologies, along with the innovative teaching approaches required to make these complex subjects accessible and engaging. The title of her talk is Quantum Physics and Quantum Technologies, New Teaching Approaches. Welcome, Professor. I would like to welcome the chair of today's session, Professor Arvind Kulkarni ji, a senior member of IAPT, Professor P.C. Deshmukh, another senior member of IAPT. And I would also like to welcome all the dignitaries and participants joining us today. Your presence is greatly valued. So before I hand over the mic to Professor Arvind Kulkarni ji for further proceedings, I would like to give a brief introduction of him. He's a distinguished scholar and passionate educator, and he has made significant contributions to the field of physics and science education. Dr. Kulkarni completed his MSc in nuclear physics from Bombay University, followed by a PhD in astrophysics from Osmania University, and he further expanded his expertise with the postgraduate diploma in higher education from the IG Open University. A dedicated learning developer, science communicator, and physics educator, Dr. Kulkarni has taught across various age groups and academic levels, inspiring countless students with his knowledge and passion for the subject. His interests extend beyond the classrooms, as he is a strong advocate for promoting physics learning at all levels and integrating cutting-edge technologies into society. So he has a deep interest in history of astronomy, physics, as well as Indian knowledge systems. We welcome you, sir. And before I hand over the mic to Professor Kulkarni, I would like to invite Professor Ahluwalia to deliver his opening remarks. Then over to you, Arvind Kulkarni ji.
So thank you, Sapna. I'm really delighted to have Ma'am Gesche, I hope I am pronouncing it correctly, for delivering this wonderful lecture. I think this is the most appropriate time for having this lecture for the IAPT community. I think we could not have asked for a better title and the better topic for today's evening. We have with us Professor Kulkarni, who is the chair for this session, and two very distinguished physics professors who have been teaching quantum mechanics to the generation of students in India, I would say. One is Professor Ghatak, and the other is Professor Deshmukh, very learned quantum teachers, I would say. And I think we are going to have a lovely session in their presence. And we have in Professor Arvind Kulkarni, a passionate teacher, educator, and I think he is the person who has been, for the last 1 year, pushing for the latest technologies to be adopted and adapted by physics community in IAPT and in the country itself. I think it's a pleasure to have him chair this session. So thank you very much, sir. It is over to you.
Yeah, it's my great pleasure to be able to chair the session. I think it's a great honor, especially because quantum physics and quantum technologies. I have always been saying that India should upgrade itself as far as this technology is concerned, and the process should be fast enough. I'm also curious to know that Professor today's guest lecture he wants to introduce quantum physics even at the school level. I think we made a beginning. Professor P.C. Deshmukh spoke about it a year ago, and this is going to be important. So, introduction of quantum physics and quantum technologies in the Indian learning environment is going to be extremely important. And this talk, I'm looking forward to with great expectation as to what we can learn from the German experience. And with these words, I'll pass on the thing to Professor Sharma. Yeah.
Yeah, thank you, Professor Arvind Kulkarni ji. And may I request Professor Gesche to please start the session.
Okay. Many thanks for your kind invitation, and the honor is quite on my side to being able and to be allowed to talk to you about my favorite topic, quantum physics and quantum technologies for teaching and learning. I will first, I will give you a short overview. I will shortly talk about the second quantum revolution, which gives the framework. Then I will talk about some basic educational foundations. And then the main part will be a proposal of a modern teaching approach. And in the end, I will indicate how one could combine quantum theory, teaching quantum theory and teaching quantum technology. So as you alluded to, it's quite important to have teaching quantum physics, I think, out of two reasons. The first reason is that quantum physics has changed the physical worldview, and it was very quickly, the mathematical foundations were very quickly found. But the conceptual physical questions led to long-lasting debate about interpretations, which made it also difficult to teach about it. But recent theoretical and experimental fundamental research enabled many applications. There are, of course, well-known and much used applications like laser and transistor today. But we go forward to the real quantum technologies, which was is now called the second quantum revolution. And I will go a small step back to the conceptual physical questions that have been attacked since the 1980s. There was the question about the nature of quantum physics, and in the 1980s, the technological possibilities grow so much that one spoke about experimental philosophy, because basic questions could now be attacked experimentally. And there were the key result, the theoretical result, the Bell's inequality as a criterion for distinguishing between classical and quantum physics and the classical and quantum physics worldview. And then came the experimental support for those equations, really the possibility to decide on the criterion Bell found. And so this led in the long run to the Nobel Prize in 2022 for experiments with entangled photons, proof of the violation of Bell's inequalities, and pioneering quantum information science. And these were the three people who got it. It was Alain Aspect, Joseph Clauser, and Anton Zeilinger. And you see also that it took 50 years from the first experimental demonstration to the Nobel Prize. And you see it's a long distance, and which is also nice for students to see that physics knowledge is growing slowly and has to develop over time. And so the second quantum revolution came quietly, driven by the questions about the foundations of quantum physics and its significance for our understanding the world, but not because the people who did those experiments wanted to develop specific application. They wanted to really understand the world, and they gained knowledge with unexpected effects. Classical instruments led to the discovery of quantum physics, the first quantum revolution with laser, transistor, and so on. And quantum physical experiments in instruments like laser and so on led to the second quantum revolution. Quantum sensors we are developing today, quantum metrology, quantum information science, and so on. And all this now led to a big, huge research area where you see the big development. I made a Google search on publications on quantum computing, quantum computers, quantum cryptography, and post-quantum cryptography, you see. And you see there was, from the 1990s, a huge increase of those publications, also indicating that there will be no job profiles in quantum physics and quantum technology, which is very interdisciplinary, has computer science, needs engineers, and so on. We will come later to that again. And there are huge implications, not only from the scientific point of view, but also from the economical point of view. The EU gives 1 billion euro in the next 10 years with more than 5,000 projects and people involved. And so you see it's a huge impact of quantum technology. And the quantum computers, above all, those quantum technology techniques inspire the media, which say mind-blowing, what is a quantum apocalypse, and also where qubits entangle with commerce, indicating that it has not only scientific implications, but also economical implications. And the scientists really try to find possible areas of application, prime factorization, simulation of drugs, calculations. But there are also limitations for quantum computers, which have to be seen, as there are only a limited number of available algorithms. And this leads to the thinking that the quantum processor could be kind of a co-processor of classical computers. But that's still the future, and much research has to be done in this respect. And so quantum technology presents challenges for physics education research. We need basic research on learning quantum physics. How do students learn and understand the core concepts? How should a modern curriculum in quantum physics look like? We have at school, at high school, at college, and so on. And we have to develop and test course modules, materials, and so on. And we need really quantum physics teaching on all levels, on school level, especially for general education, for the whole society who is attending school, future physicists as well as future historians, future hairdressers, and so on. And although, of course, on the university level for physicists, we are used to teach quantum physics for physicists, but we will have to teach quantum physics also for engineers, for computer scientists, and so on, if we really want to make progress in quantum technologies. And so I come to the educational considerations. Often quantum physics is regarded as weird and counterintuitive. It is seen as strange, but some are already be careful and to say that quantum theory really can explain reality, and that perhaps we have to change our intuitions. And I think that's the way we should go. Quantum physics isn't quite magic, but it requires an entirely novel set of rules to make sense of the quantum universe. And we have to be aware of those rules, and we have to use those rules in our thinking and in our teaching. And if we teach, we have to be aware of the different levels we want to reach. Perhaps there are some students we want only that they are aware that there is kind of quantum world, that they know, that they develop interest, and that we can discuss visions with, which is perhaps also for outreach. And there is a level where we want to reach meaning and understanding of students, being able to describe and explain quantum concepts. And we perhaps want to have a more proficient level with applications where the use of quantum concepts for understanding, explaining quantum technology is done. And if we want to design a teaching and learning environment, we have to be aware of the level we want to reach with this environment. And so we have overarching goals of all our in teaching quantum physics. It's the students' development of a modern physics worldview, addressing general education, awareness of the meaning of reality, determinism, causality, and so on. Really understanding the characteristics of quantum physics, and also have some glimpse, more or less, depending on the level we want to reach, of the mathematical description, which is really necessary, and use modern approaches to quantum physics as opposed to those more traditional approaches of teaching quantum physics we have. So we want to convey that quantum physics is a regular physics theory. There's nothing weird, nothing miraculous, but just quantum physics theory relying on experiments, having a theory, a mathematical description, having a concrete problem, and having many applications. And this applies to the first quantum revolution as well as to the second quantum revolution, where we have also theory, experiments, applications as every other physics theory. And we need quantum physics for general education, really as a complementary world description, complementary to classical physics, where the students see professional career opportunities, where we have a high demand for specialists in quantum physics, and where we really have the goals of general education, the awareness of the nature of physics, which is important, and the competence to reflect on reports in popular media. As you said, as it was in the media, the reports on quantum computer, citizens should be able to distinguish that and to reflect on it. And so we come to teaching. If we plan a teaching learning environment, we have to have several perspectives into account, as you see at the model of education and reconstruction. It's a scientist perspective, it's the science content we have to understand very well. It's the students' perspectives, it's the interest and students' conceptions and students' learning difficulties we have to take into account. And out from these two perspectives come the design of a learning environment. And if we test and evaluate the learning environment, we come back to the content perspective and to the student's perspective. And so we have a kind of circle. It goes up from the clarification of foundations, going to design of learning environment, and then with the experiments to go back. And so we develop our learning environments and courses. And so we start now with the content perspective and go to the student's perspective, and then I will have the proposal. So there were a few short time ago, there has been Delphi study on what physics researchers, physics education researchers, and high school teachers think important for teaching quantum physics. And here you see in the upper, the most important, and the lower, the less important. And you see how many people and how many groups really thought it important. Here, the more people, more groups, here less. And you see here, I took those who had quite high homogeneity and a high prominence. And you see it's superposition, it's the Heisenberg principle uncertainty, it's the entanglement, and it's the quantum measurement. And so starting from this Delphi study, we have those four concepts as central concepts for teaching as the core concepts. It's first of all, it's the superposition. Quantum states are elements of a Hilbert space, and all general states can be built as a linear combination of the basis states of this Hilbert state. And this gives the linear structure of quantum physics, which is important for all other things. You could say that the superposition is a real core, and all the other concepts follow from this. Nevertheless, it might be good to have kind of specifics. So we take the measuring process. I really talk about the process in quantum physics because it's important for understanding and distinguishing classical and quantum measurement. And the measuring process in quantum physics can be represented as a projection on the basis states or eigenstates of the corresponding operator to the physical quantity we want to measure at that moment. And what is the most important aspect is that it produces an unpredictable change of state of the quantum object. It really changes the state. It not just states it, it changes it. And this is a kind of an active role as opposed to measurement in classical physics. The next is the uncertainty together with the Heisenberg principle. which relies on the fact that physical observables are represented by operators on the Hilbert space, and that non-commuting operators, that is important part, lead to mutual non-existence of values of corresponding physical observables. And this means there are no fixed values for all physical properties at the same time. The physical properties may need different measuring apparatus. We could state it also in this way. And the fourth is the entanglement, which is very important for quantum computers and other and quantum sensing. It might also be important. And the mathematical basis is that entanglement quantum systems are described by the tensor product of the Hilbert spaces. And it means that entangled states imply that the parts of the system cannot be separated and not be treated separately, but in the whole thing. And if we put all this together, we come to the kind of the core of the difference of classical physics and quantum physics and the core of the difficulty of understanding it. We have here the mathematical basis, Hilbert space, operators, tensor product, and the corresponding physical concepts, superposition, uncertainty, entanglement. What I did not mention up to now was Schrödinger equation. But we have the Schrödinger equation describing the temporal development of a quantum system, and the Schrödinger equation is deterministic. And this is kind of the view on the quantum objects themselves. But if we want to know something about the quantum object, that's the epistemological view, we have to measure them. So we have the measuring process. And the measuring process is random. It's completely random and completely unpredictable. And this, you see, the deterministic development of the Schrödinger equation is in stark contrast to the unpredictable measuring results we have. And here you have the core of the discrepancy of classical physics and quantum physics. This difference between the ontological and the epistemological view on quantum objects. And we don't have this difference in classical physics. And from this clarification of the basics of quantum physics, very in a nutshell, we come to the students' learning. Normally we teach at university or at college with a kind of position-first approach. We start with position and momentum, and as we do it in classical physics. And this approach has a certain specific learning difficulties. And the central problem is, because we start in a similar way, it's the interference of classical properties and quantum properties. And that's very difficult to remove, because it leads the students to an unreflective use of classic terms such as particles or waves, which can create misunderstanding. And there might arise the idea that an electron is both particle and wave at the same time. And we have argumentation patterns. Electrons are at a specific location at any given time. Its trajectory, we don't have it in quantum physics. And it's only practical difficulties in determining the position at all times, not a fundamental impossibility. And there were arguments with the accuracy of the measurement and the Heisenberg uncertainty relation. And so students go to ad hoc explanations if they really have difficulties to bring classical arguments together with quantum arguments. And so it's not a very satisfactory way. So we have to think about another. There are further problems with the basic concepts we have. A measurement and probability, if we have a position-first approach, there could be confusion with time evolution, a mixing of classical aspects and quantum properties, dissatisfaction with the causal description by probabilities. We can't predict the measuring results, and the probability is only seen as an inaccuracy and not as a basic property. Uncertainty is often coupled with wave-particle dualism, and it's more interpreted as ignorance or cannot be measured instead of the non-existence of different physical quantities. And entanglement is often confused with superposition. Because of teaching, perhaps, students only consider cases of maximal entanglement, and they think of entanglement as a possibility of an instantaneous action and of faster than light action, which is also not wrong, not correct, it's wrong. And so the students, one has to have a view on this if we are teaching entanglement. What we did was we have a small questionnaire on understanding of the measuring process, and we tried it with several groups, teacher students, 46 teacher students after attending a traditional lecture on quantum theory, and we had high school students after attending a two-state approach, a modern approach via polarization. I will shortly describe it later. And you see the difference in the understanding. You see that the traditional lectures on quantum theory had some amount of students with a more or less classical thinking, which we didn't have in the group attending a two-state approach via polarization, who were more on the quantum thinking side. And this is very promising for the two-state approaches, that some of the difficulties we have with the traditional approach just disappears if we use a two-state approach. Nevertheless, also in two-state approaches, we have to be careful in teaching because students have to be aware that we can change the basis of a given state without changing the state. That's really students have to use to get it. And there might be some confusion about notation of physical interpretation. And so we really have to have several aspects we have to be aware of also if we teach two-state approaches, which is also one of the possibilities. But if you look at this, is more on the mathematical side and explaining the change of a basis and seeing that you can have the same state represented in different bases is kind of a method you can clarify to students inside quantum physics. There's no interference with classical physics. That's the important point. And so we may go to an approach to teaching, kind of a spin-first approach, and we will see we would not only necessarily use a spin-first approach, but a two-state system approach. And those two-state systems have a big advantage. They are mathematically relatively easy to access because you just have a two-dimensional state space. It's a complex space, it's a complex Hilbert space, but you can even reduce that to a real two-dimensional space if you don't have the mathematical tools. And you have the possibility of representing the states with a Bloch sphere, which you have here. The points on this sphere are the possible states of a two-state system and all the possible states. And you can explain the qubit. It's a 0 qubit and it's a 1 qubit. And you can explain the difference between classical bits. It's only 0 and 1. It's only the both North Pole and South Pole, so to say. And the qubits can have all the states, the whole on the sphere, which is very important. And two-state systems are physically meaningful in many examples. They are relevant for recent and future applications, and they really have advantages for learning as you can go straight to the core concepts of quantum physics. And you have several examples you can have. There's a double well approach you can teach as a two-state system, including Schrödinger equation. You have the polarization as a model for a two-state system. You have single photon approach with which also uses two-state aspects, and you have the interlacing of two-state systems and the quantum technology of quantum cryptography in interlacing the application with the foundations of quantum physics. And these two-state approaches can be done with polarization as a model for spin. You can write it in different modal representations with arrows. You can use kind of Dirac notation, horizontal as H, a vertical state as a V, a diagonal state and diagonal minus, D plus and D minus, D minus. And here you have the general notation 0, 1, or plus minus for the spin Z component would be this, spin X component would be that, and you would have the spin or as the modal polarization. So you see that you can use different representations that give the students kind of several viewpoints, several anchors they could use. We tried it with high school students, and they really appreciated having this concrete mathematical notation. You use this Dirac notation as a language because it's kind of a pictorial representation. You can use the Bloch sphere or Bloch circle with corresponding colors as a visualization, and you can use the Dirac notation as a technical tool for calculating probabilities and so on. And so we have important aspects for teaching. We really have to emphasize the use of models, that we really describe quantum objects with models. We describe the measurement result, we represent the states. We don't say the quantum object is, we describe and we represent. We are clear about the language, classical measurement, quantum physical measurement process, where we are very clear, and we use state function instead of wave function, and we really use multiple representations from mental images. And so we now go to the teaching sequence. We have existence of single photons. It's in 5 steps. Existence of single photons, we need that. Interferometer and double slit, superposition and measurement process, uncertainty and entanglement, with some additions and precisions I have here. Now we start with 1 and we go through to 5. The first is the generation of single photons. We generate photons by parametric down conversion. It's the tool we also use to produce entangled photons, which is written here. But first we use it for identifying photons, and this we do in such a way. We have a laser, we have this crystal, and we can have 2 photons coming out, and then we have here kind of a signal, and we have 2 detectors, A and B. Those click simultaneously, and if we divide the A detector into 2 detectors, only one of these is clicking at the same time. So we have kind of a signal who gives us the click, and then we know there's one object. It is never divided. So we have photons as individual quantum objects. And this is how it looks in reality with all the optic devices we need. And so we have photons are prepared out of the light. Photons can be detected by single detector clicks. They are indistinguishable and they must be described with help of quantum theory. And we can investigate them with using Mach-Zehnder interferometers, where we come to the second point. The whole family of Mach-Zehnder interferometer, where we have the state of quantum objects, the superposition of possibilities, and interference. Here we have a Mach-Zehnder interferometer. The state of a quantum object could be arm 1, arm 2, where it goes through to the detectors, or we have the double slit, slit 1 or slit 2. So you can treat the double slit as a two-state system. And those two possibilities determine the behavior of the quantum object. The superposition of the possibilities can have the metaphor of the catalog of possibilities, going back to Schrödinger. And we have interference. We have to distinguish between slit 1 plus slit 2 and then the probability density, or slit 1 probability plus slit 2 probability, where the two slits are distinguishable. And so this is an important tool for analyzing quantum objects. And there are many simulations you could use, and you have here also a simulation. It's from St. Andrews University, where you also have combined with the physics, optic devices, you have the mathematical description. How do you describe these devices mathematically in quantum physics? And then you can proceed further and really see how do quantum objects work. It's a delayed choice experiment, or it's a rich ray information. All of these have meanwhile really experimental realized, so they are no longer thought experiments, but they can really be done. And all the rich ray information you can do in a real quantum experiment and in a model experiment with laser, where you have the double slit here with two polarization polarizers, where you can control the polarization direction, and really marking the slit causes the interference to disappear, and deleting the marking with a third polarizer you have here really enables the interference again. It's a very nice experiment and can easily be done. And so we come to the important and fundamental characteristic of quantum physics. It's a superposition. You have the A detector we had before with a beam splitter over here, and at the beam splitter the photon can be reflected to the AR, or it can be transmitted to the AT, and only one clicks at the same time. We had that already, but we can't predict the sequence they are clicking. And so we have the photon state as a two-state system described, and we have the random measurement results we have here. And so we can say that the measurement process, as I already said, the measuring apparatus determines the possible results, and the entire experimental setup determines what can be seen. And in the measurement process, a superposition state becomes a basis state, but a basis state is retained. And so we could say that the measuring process results in resolving the superposition. That's quite important. And I think I will skip this. I go to uncertainty. Also here we can have a model experiment with polarization, where we have here polarized photons. Then we have two calcite crystals turned relatively to each other in such a way that on the screen here you come in with D plus photons, you do some measurements, kind of measurements here, and you result with D- photons you have here, implying that you can't ascribe the photons here a fixed value of polarization because it doesn't has it because we arrive here also with D-. That's the principle of uncertainty we can have. And perhaps you know the experiments with cross Stern-Gerlach apparatus, and there you use not polarization but the spin. And if you have the physical description, there are no fixed values for all physical properties at the same time, which is very important, and that a physical property is only realized in the measurement process where it is given a fixed value. That's the center of the uncertainty we do have at this point. And sometimes you read about complementarity, and complementarity is often used with a focus on epistemological or philosophical issues, which according to Bohr, meant that the complete description of quantum physics phenomena requires two different aspects that are mutually exclusive in classical physics. You need two aspects to describe the whole behavior, but classically they are excluding each other, and that's the complementary description in the sense of Bohr. And we come to the entanglement. We have a thought experiment we could do with Schrödinger's cat, or the famous EPR experiment, and the observation gives that the results for Alice and Bob, the measurement results themselves are random, but Alice and Bob, for instance, have always the same measurement results. They only don't know which one. And this means, this implies that there are over-statistical correlations between all these measurement results. That would be the fifth step, where we could, one could go to the EPR experiment, treat the Bell inequality in Greenberger-Horn-Zeilinger states, or also treat quantum teleportation as an application of entanglement. And what is important with entanglement is it is non-separable. We have separate spatio-temporal areas that must be considered together. That is one point. And we really have to describe the state of the whole system cannot be described by means of the states of the two individual objects and their relations. And so this is really kind of, you have to get used to it, that you can think of two different physical quantities or different parts which have to be treated as one whole. And therefore it's also sometimes described with the word of holism. So now I'm gone very quickly through the most important things we have. And now I want to close with how we could combine the core concepts of quantum physics and quantum technology. And there the question arises, which technologies are in which way suited for reaching the goal of introducing high school students to the basics of quantum physics and to applications using them? And here we go back to the four core concepts we had: superposition, measuring process, uncertainty, and entanglement. And you see that there are applications from quantum technology, such that quantum cryptography, which uses the randomness of the measurement result to generate a perfect random sequence you need if you really want to have a secure encrypting tool. You need a perfect random sequence. You have the security of communication. Because of uncertainty, it's a BB84 protocol, and even a spy cannot outsmart the law of nature, the uncertainty. So you really use the quantum properties for having secure communication. The quantum teleportation also says It says do not measure because the measuring process changes the state of the system, but entangle. Entangle two different photons, and then you can really transfer the information of the photon from one photon to the entangled photon on the other side. And you have the quantum computers, which really need all of these. They need entanglement, they need superposition, and they have to be aware of the measuring process. So quantum computers are really having all the needing all the core concepts of quantum theory. And if you want to really to decide what would be suitable for teaching, then I did research on the interest. The interest I measured with YouTube calls of videos. I said, how well can I reduce the complexity, elementarize for high school, for instance? How clear are the core concepts of quantum physics visible in this application, and how relevant are the core concepts for this application? And I made a weight between 1 and 4 the degree, and I weighted it, what is the most important. You could change all this. And when I summed up, I had quantum teleportation and quantum cryptography as perhaps most suitable to combine the core concepts of quantum physics and quantum technology. And this is what I said to you already in the beginning. You have the encrypting procedure. You interlace with a two-state system. You have the generation of a quantum key where you also need the two-state system, the possibility of superposition, and the properties of the measurement process. All these you need for the generation of the quantum key. And for the secure exchange of the key, you need also the properties of the measurement process, and you need uncertainty for the BB84 protocol. And you need it also for the discovery of an eavesdropper. And so you see how the core concepts interlace with the steps of this technology. And you can do it similarly with a quantum computer, where you have the processing of information in the qubits, superposition. You need the logic gates, you need the unitary time evolution that you need in the quantum computer. In the algorithm, you need the quantum gates, and you need the entanglement of several qubits if you want to do that. And for the result of computation, you have to be aware of the properties of the measuring process. You only get probabilities and no predictable results. That's important to have into account. And so if you have the quantum technologies as a bridge between general education and professional orientation, students could get some insight into possible framework of research. They see fascinating applications, and perhaps they also see the possibilities of professional career. So you can really use quantum technologies as a vehicle to really convey the quantum physics and the quantum physics worldview, and to use this quantum physics worldview for really interesting applications. And so many thanks for your attention.
Thank you, Professor. Thank you, Professor Gesche. It was wonderful talk. Over to
Thank you.
you, Professor Arvind Kulkarni ji.
Yes.
For summarizing this.
I think it was a wonderful talk indeed. I was expecting some of it as it was mentioned in her brief biodata. I feel that slowly quantum science and quantum technology should make entry into our schools. By schools, I understand standard 8 onwards, 8, 9, 10. Of course, by 10, they already learn something about, hydrogen atom and all that, but not in detail. but a certain amount of ontological, epistemological thinking needs to be introduced at the earlier level also. It is not true that students do not understand. Students are not exposed to it, therefore they don't understand. And we teachers have to put one step forward, saying that modernizing education is extremely important. This will help. I would suggest that at least 20% of what physics we teach at standard 8 should be converted into quantum science and quantum technology, so that by the time they come to 10, that is, they finish their early schooling, they will have some idea about what is happening. The reason is twofold. One is it requires philosophical depth, which can be introduced, and also there is a technological relevance as far as the jobs and other things are concerned. So my particular feeling after this particular talk was definitely that we should inject modern science as well as technology. Another point I wanted to make is for a typical student, because I was a student, school student almost 40 years ago. So the things are different now. Now, how to connect classical and modern things? I feel that the concept of standing waves, we teach them waves nevertheless. The concept of standing waves, I think, is a precursor to quantum thinking. I'm not saying the standing waves on a spring or on a stretched wire is all quantum, but it definitely introduces the concept thinking that between two fixed ends, if you stretch a wire, depending on the density, you will have number of nodes and antinodes. So this can be some kind of a precursor, so that we are able to connect to the classical physics and the modern physics. Then of course they learn in the standard 10 what they regarding hydrogen atom and all that. The other things come later, but they need some connector also, connection between classical to modern physics, so that they will not feel totally out of place. The concept of deterministic and non-deterministic thinking needs to be introduced, though it will be on a pilot scale. It has to be done, because all measurements will not give you the same result. Of course, the error bars apart. We need to introduce some philosophical concepts also, and we need to be bold in this area to introducing scientific thinking procedures to students. With these two remarks, I would like to end my impression, thanking Professor Gesche for speak for her wonderful presentation, and I think there are many others who would like to comment on this. I will expect Professor Deshmukh I would like to hear from him, Professor Kagli, Professor Ahluwalia, and others. Thank you very much. Thank you. Great.
Thank you very much for your nice words. I very much agree to you that the students should learn quantum physics at a relatively early age. And one PhD student of mine is developing a teaching unit really for students aged 15. And it was really evaluated, I think, positively. It's not quite finished yet, but it really looks good that you can really teach the first steps into quantum physics at the age of 15. And I think it can really be done. And so I want to support you to say we have to start early to teach quantum physics. And I think the students should be aware about the difference. There's a classical thinking, and they perhaps have to be really aware what is the characteristic signature of classical physics and what is the difference to quantum physics, and really to accept quantum physics as it is and to think and reason quantum physically. As in teleportation, you need really to think the quantum physics way. If you think the classical way, you can't reach the solution. You really have to accept the quantum concepts and to reason in this way. And that students have to get used to it, and also therefore an early start in learning quantum physics would be really good.
Good. Yeah.
I'm not able to see any question in the chat box.
Kagali has there's a sign of Kagali.
Yeah.
Yes.
Thank you very much for a very nice introduction. I would like to know how you are going to introduce or explain the measuring process to students, wherein we require the interaction between classical and quantum systems. The measuring system, measuring process, where does it end? How do you introduce the measuring process? A very critical thing.
The measuring process is really a change of the state. If you have a quantum physical superposition state, you end up in one of the basis states. I do not go into the detail how this process proceeds, but I skip the decoherence. I would like to really teach the students the decoherence, to say that the quantum system entangles with the measuring apparatus, and if this entanglement resolves, we get at a single solution. So decoherence can explain the process, but it cannot, of course, also not predict which value will be taken. That remains kind of a mystery. You can't explain it, you just have to accept it.
Thank you.
Please.
Professor Aluwalia has also raised his hand. Sir, please unmute yourself.
Thank you very much, Professor Gesche, for a wonderful lecture. I think it was a very intuitive lecture. I really enjoyed listening to it.
Thank
and
you.
The way you correlated the concepts with the quantum technologies, that was remarkable in a very simple fashion. I think that was another highlight of this lecture. And the best part, which I think has emerged out of this presentation, is this, that if you start with a toy model like taking spins via Stern-Garlick experiment, that is makes a lot of interesting sense in relating these very, very, non-intuitive concepts with the reality. I think that was a very interesting experiment which was done at a time when we were looking for the quantization of the angular momentum itself. And this was just remarkable. I have just one, question, and that is this: that is it possible that just by abandoning Schrödinger equation approach, we can follow this Dirac's notation approach and do everything which we need to do for understanding the quantum technologies of today?
I think you can do a lot if you use this Dirac notation approach. For students, even at not so a high level, it is very intuitively. They just accept it if you teach them the Dirac notation, and you can really work very intuitively with this Dirac notation. Sometimes you also need the vector notation in the vector space. You need the column vectors. Sometimes you have to switch between those two. But you, as a pictorial representation of what is going on, and also teaching something like a no cloning theorem I didn't talk about today, the Dirac notation is quite sufficient and gives the students kind of insight, kind of concrete basis where they not only have the words, but also concrete mathematics. They can calculate something. And sometimes it's good to complement it, especially if you want to treat several bases. It's good to have the vector notation as a column vector in two-dimensional space in addition.
It is like, now going from classical to then we started talking about modern physics. And now I think we should talk about ultra modern physics by this approach.
Yes.
We should really think of that kind of a situation now. And
Yes.
your very, interesting study which you have made using physics education research, that was also very insightful. Thank you very much for a
Yeah.
beautiful.
Thank you. I enjoyed talking today. Thank you.
Yeah.
Yeah, Professor Deshmukh has raised his hand.
Yeah, Professor Gesche, thank you very much for a very exciting talk, a very insightful talk. We learned a lot, and in such a short time, you brought out an outline of how best one can communicate very difficult concepts to students. I wonder what I would like to have your thoughts on the following suggestion. If it is all right to completely stay away from epistemological and ontological aspects of quantum theory in the early introduction of quantum mechanics, but simply suggest to students that yes, it is a mathematical theory which works, whereas classical pictures which are intuitive do not represent nature correctly. And this is the mathematical structure, and this is how it works. And go ahead and introduce quantum mechanics as a mathematical theory.
I would not go as far as to say we should introduce quantum physics at an early stage as a mathematical theory. I think we should always, I think it is important to make the students first clear what is really the signature of classical physics. It's not very clear to many students. The reality, the causality, and determinism, they are just...
Absolutely. I was thinking about introducing the mathematical structure after we tell them about causality and determinism in Newtonian mechanics. So introduce them to causality and determinism in Newtonian mechanics, and then tell them that that is not how nature works, because it is impossible to make simultaneous measurements of position and momentum.
Yes, and the mathematical structure, especially if you take something simple as Dirac notation and the use of Dirac notation, and depending on the level, also to proceed. But even at an early stage, the mathematical structure gives the students kind of help and confidence, and that what they are thinking is correct. It's more concrete and therefore helpful in learning than, I say, verbalizing and trying to describe everything by word. You need kind of concrete anchor where they can stick to.
Yeah, I
And
think so too.
therefore you need kind of mathematics, but to be introduced very carefully and very slowly.
Sure. Yes. Thank you.
So,
I have a follow-up question. Perhaps at a later stage, means after introducing Dirac notation, Schrödinger equation, uncertainty principle, and even entanglement, and so on. At what point, if at all, would you like to introduce certain intriguing ideas like discussion on collapse of a wave function, Wigner's friend, and Wigner-Neumann interpretation of measurement and so on? These are very complex concepts.
Yes. I think I have left teaching complex situations like weakness, friend. And I like more to think about the measuring process as dissolving superposition in the sense of the coherence than of a collapse of the wave function. I try to avoid this term. Sometimes, of course, I explain it to students because you find it everywhere in the literature, but my wording would more be dissolving the superposition, really changing the state, an active role of the measurement. That would be my approach after thinking about it. I present the students several interpretations, several possibilities of solving the measurement process. And sometimes I also mention weakness, friend, but it's no main role. It's more the acceptance. How does measurement work in quantum physics? How can we understand it? How can we work with it? And that the active part or the dissolving and the decoherent sense, that is the way I talk about measurement.
Yeah, thank you very much for your answer, because I find in it an endorsement of what I have been doing, and I was worried if it was all right. So I'm really glad to hear your answer. Thank you.
Please.
There is one question from Malesh. He's asking, is it better to try out a package course in quantum basics for a set of students at high school who are interested in physics?
A package course? What?
Packaged course in quantum basics for a set of students at high school who are interested in physics.
Yes, I would really recommend to do that, because students at high school are very interested in quantum physics, and I would really I would really try it out, and really I think the students will enjoy such a course on quantum basics. Yes.
Yeah, and there is a comment from Professor Kulkarni. We should introduce quantum concepts and math structures early enough at standard 8, 9, and 10 so that they get used to it.
Yes, I would completely agree to that. I would completely agree to that. As I said, we tried it with grade 9. I think it's the same with you. It's a 15-year-old, and it really works.
Yeah. Yes. So we don't have any more questions in the chat box, and just comments that the talk was wonderful and informative.
Thank you very much.
Yeah.
Thank you very much.
So is there any question? Anybody wants to ask any question? Should we close it? I think there's no. Yeah, there's no.
It would be very nice, because I have to leave now also for the next date I have. So it was wonderful being with you. I enjoyed really the interesting questions and really enjoyed it a lot. Thank you.
So we are thankful to you, Gesche, and we hope that we will meet in future and we'll be able to collaborate and do something together.
Yes.
Right?
Thank you. Looking forward to it.
Yeah. Thank you, everyone. Thank you, everyone. And
goodbye.
Good night, and see you at our next event.
Thank you.
Goodbye.
With this, we come to the end of this session. Thank you.
Thank you.
Thank you, sir. Thank you, Professor Arvind, for chairing the
Thank
session.
you. Thank you very much. Thank you. Great.
Thank you, sir.